Welcome to Creata classes. In this lecture series, we will cover the altitudes. We have divided the lecture series into two lectures. In the first lecture, we will cover the altitudes and the orthocenter, and in the second lecture, we will cover the orthic triangles. Let's begin with the altitudes. Altitudes are the perpendicular line segments that join the vertex with the opposite side. Let's take a triangle ABC. Let's draw the perpendicular line from the vertex A to the opposite side. This line segment, that is AD, is the altitude for this triangle ABC. A triangle is having three vertices, so a triangle can have total three altitudes. Let's draw the altitudes from the vertex B and C. Both of these line segments are perpendicular to the opposite side. So we can say all these three line segments are the altitude for this triangle. Got it? Very simple. Let's compare these altitudes with the other line segment of the triangle, that are medians, angle bisectors, and the perpendicular bisectors. Medians, we know medians are the line segment that connect the vertex with the midpoint of the opposite side. The median connect with the midpoint of the opposite side. And the angle bisectors divide the angle into two equal parts. These are the angle bisectors. And the perpendicular bisectors bisect the sides of the triangle, as well as these are perpendicular to the sides of the triangle. They bisect the sides as well as they are perpendicular to the side. The perpendicular bisectors are somewhat similar to the altitudes of the triangle. But there are some difference between both of them. Perpendicular bisector bisect the sides of the triangle as well as they are perpendicular to the sides of the triangle. While the altitudes of a triangle are just perpendicular to the sides of the triangle, they do not bisect the side of the triangle. Perpendicular bisectors are perpendicular as well as they bisect the sides of the triangle, and the altitude only are perpendicular to the sides of the triangle. For more clarity, in the same figure, we will try to draw the perpendicular bisectors as well as the altitudes in a triangle. Altitudes are already drawn in this triangle. Let's try to draw the perpendicular bisector. First of all, let's locate the three midpoints of the sides of the triangle. D dash, E dash, and F dash are the three midpoints of the sides of the triangle. The line segment which starts from these three midpoints of this triangle as well as perpendicular to these three sides of the triangle are the perpendicular bisector. These three line segments marked in the red are the perpendicular bisector, and these three line segments marked in the blue are the altitude for this triangle. Now I think you will be able to clearly differentiate between the altitudes of the triangle and the perpendicular bisector for the triangle. Got it? Let's move to the next concept. Are you able to observe the three altitudes of the triangle are intersecting at a common point? And this common point is known as orthocenter. It is generally denoted by H. Okay, this point is the orthocenter. The intersection point of median is the centroid. Intersection point of the angle bisector, it is incenter. Intersection point of perpendicular bisector is circumcenter. And the intersection point of three altitudes is the orthocenter. Okay, are you able to visualize and compare all these fundamentals? Moving further, let's see some angles of these altitudes. This angle is angle A. Further, these angles are 90-degree angle. Further, are you able to visualize the quadrilateral AEHF? Okay, this is a quadrilateral. And we know the sum of four angles of a quadrilateral is 360 degree. So let's add all these four angles. This is angle A and these two angles are 90-degree angle. On solving, we got this angle, that is angle FHE, as 180 degree minus angle A. Further, the angle FHE and angle BHC are vertically opposite angle, and we know the vertically opposite angles are equal to each other. So can we say angle BHC is also equal to 180 degree minus angle A? So this angle is A and this angle is 180 degree minus angle A. So we got angle BHC is equal to 180 degree minus angle A. Similarly, can we say angle AHC is equal to 180 degree minus angle B, and angle AHB is equal to 180 degree minus angle C. Okay, got it? In other words, we can say angle at the orthocenter and the opposite vertex are supplementary. Sum of both of these angles will be equal to 180 degree. These are the angles at the orthocenter. We can compare this angle with the angle formed at the circumcenter and the angle formed at the incenter. We have seen in the incenters, that is angle formed at incenter, that is angle BIC is equal to 90 degree plus half of angle A. And in the circumcenter, we have seen that angle BOC is equal to twice of angle A. And in this altitude, that is orthocenter, we have seen that angle BHC is equal to 180 degree minus angle A. This comparison is very much to avoid any confusion, otherwise we will be confused. Moving further, we have studied that orthocenter is the point of intersection of the three altitudes. Now we will take the different cases of triangle and we will see where the orthocenter is formed. First of all, we will take a acute angle triangle. Okay, this is a acute angle triangle. Let's draw the altitude for this triangle. These are the three altitudes for this triangle, and these altitudes are intersecting inside the triangle. That is, the orthocenter for an acute angle triangle is inside the triangle. Let's move to the next case. The next case is an obtuse angle triangle. Let's take a obtuse angle triangle ABC. Here angle B is more than 90 degree angle. For this triangle ABC, we have to draw the three altitudes. We know altitudes are the line segment which start from the vertex and are perpendicular to the opposite side. Let's begin with the vertex B. This line segment is the altitude. It starts with the vertex B and it is perpendicular to the side AC, that is the opposite side. In similar line, we have to draw the altitude from the vertex A, which is perpendicular to the side BC. Now, how to do so? If we draw the random line segment from the vertex A to the side BC, all these line segments are not perpendicular to BC. None of these lines are making angle of 90 degree with the side BC. So how to draw the perpendicular for the side BC, which is touching the vertex A? For that, we have to extend the side BC. If we extend the side BC toward the side A, we can draw the line segment which is perpendicular to this side BC as well as it is touching the vertex A. So this line segment will be altitude for the vertex A. Got it? This line segment is starting from the vertex A and it is also perpendicular to the extended side of the BC. So we got that the altitudes can also lie outside the triangle. This is one of the important findings that we have done. Further, now we have to draw the altitude from the vertex C, which is perpendicular to side AB. We will apply the same concept. We will extend the side AB and we will draw this altitude which is perpendicular to extended side of the AB and it is starting from the vertex C. Okay, got it? So these are the three altitudes for the triangle ABC, that is an obtuse angle triangle ABC. So we got that the altitudes can also lie outside the triangle. Let's try to find the orthocenter for this obtuse angle triangle, and we know orthocenter is the point where the three altitudes intersect. Let's extend the three altitudes. We got this point. Okay, this point is the orthocenter for the triangle ABC. So for this obtuse angle triangle, the orthocenter lies outside the triangle. Got it? Let's move to our next case, that is a right angle triangle. Let's try to draw the altitudes for the three sides. First of all, let's take the hypotenuse. This line segment will be the altitude. This line segment is perpendicular as well as touching the vertex of the triangle. Further, these are the two legs of the triangle. Let's try to draw the altitude for these legs of the triangle. Are you able to observe these two legs itself are the altitudes for this triangle? These legs are touching the vertex as well as these are perpendicular to the opposite side. So we can say these two legs and this middle line segment is the altitude for this triangle. Okay, got it? The two sides of the triangle itself are the altitude for this triangle. This is the feature of a right angle triangle. Further, let's find the orthocenter for this triangle. Orthocenter is the intersection point of three altitudes. Are you able to observe the orthocenter for a right angle triangle lies on the vertex B? So the vertex B, that is the vertex having the 90-degree angle or a right angle, is the orthocenter for a right angle triangle. Very important fundamental, the orthocenter of a right angle triangle is the vertex of a right angle triangle. Which vertex? Which is having the 90-degree angle. These types of questions are generally asked in the competitive exams, so you should know it. So we got for an acute angle triangle, the orthocenter lies inside the triangle. For an obtuse angle triangle, the orthocenter lies outside the triangle. And for an right angle triangle, the orthocenter lies on the vertex of a right angle triangle. Which vertex? Which is having the 90-degree angle. Further, are you able to observe as we are increasing the angle of the triangle? Means as we are moving from acute angle to a right angle triangle and further to the obtuse angle triangle, the orthocenter is shifting from inside, then to the vertex of the triangle, then to the outside of the triangle. The orthocenter is moving from inside to the outside. And one important observation, orthocenter is moving towards the angle which is largest of the three. Here if you observe, angle B is the largest of the three angle. So the orthocenter is moving towards this angle B at the right angle triangle, and further as we increase the angle B, it is moving outside the triangle through the angle B only. So we can say the orthocenter, if it is outside the triangle, it will be behind the largest angle. Got it? Just a small observation, you should know it. It will be helpful in solving the questions. Moving further, if you got any question related to altitude of the triangle, one of the helpful formula that will help you in solving the question is the Pythagoras theorem. You can easily identify the triangles and you can apply the Pythagoras theorem to find the altitude of the triangle. So you should know the Pythagoras theorem, that is square of the hypotenuse is equal to sum of square of the legs of the triangle. So you can split the triangle and you can apply the Pythagoras to solve for the altitudes. This is one of the greatest help you can get. Further, if we take a right angle triangle with the sides as A, B and C, here the altitude which is connecting the hypotenuse is marked as P. This angle is 90 degree as this is the altitude. Further, A and B are also the altitude for this triangle we have just seen. So let's find the area of the triangle. We know area of a triangle is half into base into height. If we take A as a base, then B will be the height for this triangle, that is the altitude. Can we say area of this triangle is half into A into B? And we can also calculate the area of this triangle by considering the side C as a base. And with C as a base, we can say P is the altitude, that is the height of the triangle. So we got area of the triangle also as half into C into P, half into base into height. Let's compare both the area of this triangle. On solving, we got P, that is the length of the altitude, is A into B upon C. That is multiplication of the legs upon the hypotenuse. This is one of the formula for calculating the altitude in a right angle triangle. Got it? So we have seen that with the help of Pythagoras also we can calculate the altitude, and with the help of area of the triangles also we can calculate the length of the altitude. That is by considering the different bases, then considering the different heights as per the bases. Got it? Moving further, in the same figure, let's assume the altitude P is dividing the hypotenuse into the ratio of x is to y, or we can say the altitude P is dividing the hypotenuse into x and y. Let's see the formula. First of all, let's apply the Pythagoras in this triangle. Here A and B are the two legs of the triangle and x plus y is the hypotenuse. We got a square plus b square is equal to x plus y whole square. And if we take this small triangle, we can apply the Pythagoras in this small triangle also. Let's do so. Here the side B is the hypotenuse. Hypotenuse is the side which is opposite to 90 degree angle. Here this angle is 90 degrees, so we can say B is the hypotenuse and X and P are the legs for this triangle. So we got X square plus P square is equal to B square. Similarly, if we apply the Pythagoras in this triangle, we got Y square plus P square is equal to A square. Let's add both of these equations. We got A square plus B square is equal to X square plus Y square plus 2P square. And just now we have seen that A square plus B square is equal to X plus Y whole square. Let's replace the terms. On replacing and solving, we got 2xy is equal to 2p square. On solving for p, we got p is equal to root of xy. P, that is the length of the altitude, and x and y are the two segments of the hypotenuse that has been divided by the altitude p. Okay. So the altitude for a right angle triangle is equal to root of xy. Okay, that is the geometrical mean. Got it? These are the two formulas of altitude in a right angle triangle. Either you can remember this formula, that will be really helpful to you in solving the question, or you can remember the technique, that is you have to apply the Pythagoras in the altitude case, as well as you can use the formula of area of the triangle by considering different bases and the altitudes as per the different bases. Got it? Let's move to our next fundamental, that is the orthocentric system. A small fundamental, you should know it. Orthocentric system is a set of 4 points on a plane, one of which is the orthocenter of the triangle formed by the other 3. Means if we form a triangle from the point A, B and C, then H is the orthocenter. If we form a triangle from the point A, B and H, then the fourth left out point, that is the point C, will be orthocenter for the triangle ABH. Similarly, if we take the triangle HBC, then the point A will be the orthocenter. Got it? If we form the triangle from any of the 3 points, then the fourth remaining point will be the orthocenter for the triangle. This is known as orthocentric system. One small fundamental. Let's move further to the next concept. The next concept is that the sum of 3 sides of the triangle is always greater than the sum of 3 altitudes of the triangle. For that, let's check the triangle ABC with the altitudes as AD, BE and CF. If we take the triangle ADB, okay, this is the triangle ADB, can we say the hypotenuse is greater than the legs of the triangle? Hypotenuse is the largest side. So, can we say AB is greater than AD? Similarly, for the triangle BEC, can we say BC is greater than BE? Similarly, for the triangle ACF, can we say AC is greater than CF? If we add all these 3 equations, we got AB plus BC plus AC is greater than AD plus BE plus CF, which means that the sum of 3 sides of the triangle is always greater than the sum of 3 altitudes of the triangle. Similar kind of correlation between the sides and the line segment inside the triangle we have seen in the median, where we have seen that the length of 3 sides of the triangle is always greater than the sum of the medians of the triangle. These are the relations that we have covered in the median. Got it? This is the small fundamental. These questions may be asked in the competitive exams. Moving further, let's move to the next concept. For that, we will take the same figure, that is a triangle ABC with the medians as AD, BE and CF. In this concept, we will try to calculate the area of the triangle ABC by taking different bases for this triangle. We know area of triangle is equal to half into base into height, that is the altitude. If we take BC as the base, can we say AD is the altitude for this triangle? We got area of this triangle as half into BC into AD. Similarly, if we take AC as base and BE as the altitude, we got the area of triangle as half into AC into BE. Similarly, with AB as base, we can say the area as half into AB into CF. So these 3 are the area of the triangle ABC. Let's equate all of them. We got 2 times delta, that is area of triangle, is equal to BC into AD is equal to AC into BE is equal to AB into CF. Let's find the side of the triangle from this equation. We got BC is equal to 2 delta upon AD, AC is equal to 2 delta upon BE, and AB is equal to 2 delta upon CF. Here area of the triangle, that is delta, is constant. Okay, it is fixed for all the 3 cases. So here can we say BC is inversely proportional to AD and AC is inversely proportional to BE and AB is inversely proportional to CF? Or in other words, can we say the ratio of AB is to BC is to AC is equal to 1 by CF is to 1 by AD is to 1 by BE? Okay, we can say so, as 2 times the delta, that is the 2 times the area of the triangle, is fixed or constant for all the 3 cases. Getting the point? Here AB, BC and AC are the sides of the triangle and CF, AD and BE are the altitudes of the triangle. So we got a relation, that is the sides of the triangle is inversely proportional to the altitudes of the triangle. This is very important relation. It shows that the larger is the side, the smaller will be the altitude it is carrying. For example, if we take this triangle ABC, here BC is the largest of all the 3 sides. For this case, the altitude which is attached to this side will be the smallest. Here the altitude AD which is attached to BC is the smallest. Larger the side, the smallest will be the altitude, and the larger the altitude, the smaller will be the side. Both are inversely proportional to each other. This fundamental is used where in the question it is asked like you have to find the largest altitude or you have to find the largest side of the triangle. There we have to focus is that when it is asked for the larger side, we have to go for the smaller altitude, and where we have to go for the smaller side, there we have to focus for the largest altitude. This fundamental you have to correlate with the question. Got it? Very easy and very simple fundamentals. These all are the properties of the altitude of triangle. The questions may come in the exam based on these properties. So you should know all the properties. Let's move to next fundamental. This fundamental is a type of question. You can take this fundamental as a question. The question is, we have to identify how many cyclic quadrilateral are inside this triangle ABC with the altitude as AD, BE and CF. We have to identify how many cyclic quadrilateral we can form inside this figure. First of all, cyclic quadrilateral we have done, that is quadrilateral which is having all its 4 vertex on the circumference of the circle. And we know the property of cyclic quadrilateral, that is the sum of opposite angle is 180 degree, that is they are supplementary. This is the property of the cyclic quadrilateral. Here in this figure we have to find how many cyclic quadrilateral we can form inside this figure. Let's proceed. First of all, we know the angle at point D, point E and point F are 90 degree angle. So with the help of these angles, we can easily identify the cyclic quadrilateral. Let's see what I mean to say. Let's take the quadrilateral BDHF. Okay, are you able to identify this is a quadrilateral? Let's take this quadrilateral out of the figure. Here angle D and angle F are 90 degree angle. Means these angles are supplementary. That is angle D plus angle F is equal to 180 degree. And we know the property of the cyclic quadrilateral, that is the opposite angles are supplementary. Here angle D and angle F are supplementary. So we can say the quadrilateral is a cyclic quadrilateral. Got it? Similarly, can we say DCEH is also a cyclic quadrilateral? That is the sum of angle D plus angle E is equal to 180 degree. These angles are supplementary. So we got DCEH is also the cyclic quadrilateral. We got 2 cyclic quadrilateral. Similarly, are you able to observe FHEA is also the cyclic quadrilateral? Here angle F plus angle E is equal to 180 degree. So we got 3 cyclic quadrilateral in this. Further, can we make the quadrilateral BCEF? By joining E with F, we can form the quadrilateral BCEF. Is this quadrilateral is also the cyclic quadrilateral? Let's see. Let's take this section out of the figure. Are you able to correlate this fundamental with the fundamental of the circles, where we have seen that the arc is subtending the angle on the circumference of the circle? There we have also seen the diameter subtend the angle of 90 degree at the circumference of the circle. At every point on the circumference of the circle, the angle subtended by the diameter is 90 degree. The same fundamental we will use here. Here angle BFC is equal to 90 degree and also angle BEC is also equal to 90 degree. So can we say BC as a diameter and BC is subtending both of these angles at the circumference of the circle? So we can say BCEF is also the cyclic quadrilateral. We can say so. Got the fundamental? Here angle BFC and angle BEC are 90 degree angle and these angles are subtended by the diameter of the circle BC. Got it? Further, in the similar philosophy, can we say CDFA is also the cyclic quadrilateral? CDFA. This quadrilateral is also the cyclic quadrilateral. Here AC is the diameter and these two 90 degree angle it is subtending at point F and D. In the similar line, we can say AEDB is also the cyclic quadrilateral. Here AB is the diameter and it is subtending the 90 degree angle at point E and point D. So we got 6 cyclic quadrilateral inside the triangle ABC with the altitudes. Got it? This is a type of questions which are asked in the competitive exams. So you got the basic fundamental how to identify the cyclic quadrilaterals. Let's move to the next fundamental. In this fundamental, we will calculate the distance of vertex to the orthocenter. For that, we will take the same figure, that is triangle ABC, with the medians as AD, PE and CF. Here, we will take the sides as BC as A, AC as B and AB as C. Here in this fundamental, the distance of vertex to the orthocenter, that is AH, BH and CH, we will calculate. Firstly, let's see the formula. The formula of AH is 2R cos A. Here R is the circumradius that we have seen in the previous lectures. And BH is equal to 2R cos B and CH is equal to 2R cos C. So these are the formulas of distance of vertex to the orthocenter. We will see the proof of this fundamental. Let's see. The proof will involve the fundamental of sine rule that we have done in the previous lecture. That is A upon sine A is equal to B upon sine B is equal to C upon sine C is equal to 2R. This is the formula that we have seen in the circumradius. So this fundamental will be used in this proof of the formula. Let's see. First of all, let's take the triangle ABE out of the figure. Here angle E is 90 degree angle. Can we calculate the cos of angle A? Cos is base upon hypotenuse. Here A is the base and the side C, that is AB, is the hypotenuse. So can we say cos A is equal to AE upon AB? And we know AB as C. So we got AE is equal to C times cos A. Let's move further. If we take the triangle ADC, here this angle is angle D and this complete angle is angle C. Can we write angle DAC as 90 degree minus angle C? We know the sum property of the triangle, that is sum of three sides of the triangle is 180 degree. So we can write angle DAC as equal to 90 degree minus angle C. Further, if we take this small triangle AHE, this is a right angle triangle. Here angle E is 90 degree and this angle is 90 degree minus C. The same we have just seen. If we apply the formula of cos to this angle, that is cos 90 minus C, that will be equal to base upon hypotenuse. Here AE is base for this triangle and AH is the hypotenuse. And we know cos 90 minus theta is sin theta, that is cos 90 minus C is sin C. And just now we have proved AE is equal to C times cos A. Let's replace AE with C times cos A. On solving, we got AH is equal to C upon sin C into cos A. And here comes the role of our sine rule, that is A upon sin B is equal to B upon sin B is equal to C upon sin C is equal to 2R. Can we replace C upon sin C with 2R? Here the R, that is the circumradius, is introduced into the formula. So we got AH is equal to 2R into cos A. That is the proof of the formula. The distance of vertex to the orthocenter is equal to 2 times the circumradius of the triangle ABC into the cos of angle A. That is the vertex from where the altitude is starting. Similarly, we can prove BH is equal to 2R times cos B and CH is equal to 2R times cos C. These formulas are very important formulas and can be asked in the competitive exams. Let's move to the next fundamental. In this fundamental, we will see the relation between the altitudes of the triangle with the in radius. Just now we have seen the relation of altitude with the circumradius. Now we will see the relation of altitude with the in radius. In the previous lecture, we have denoted the in radius as small r. So the relation that I am talking about is 1 upon r is equal to 1 upon h1 plus 1 upon h2 plus 1 upon h3. Here h1, h2 and h3 are the three altitudes of the triangle. Let's check the triangle ABC with the altitudes as h1, h2 and h3. The sides we have taken as A, B and C. Let's see the proof of this formula. The proof is very simple. We have to calculate the area of the triangle ABC by considering different bases for this triangle. We know the area of the triangle is equal to half into base into height. So if we take A as a base, can we say area of triangle ABC is equal to half into A into h1? Similarly, by considering B as base, we got the area as half into B into h2. Similarly, we got area of triangle as half into C into h3. Can we rewrite these equations as 2 upon h1 is equal to A by delta and 2 by h2 is equal to B by delta and 2 by h3 is equal to C by delta. Here delta is the area of the triangle. Let's add all these three equations. We got 2 times 1 by h1 plus 1 by h2 plus 1 by h3 is equal to A plus B plus C upon delta. Here in the formula, in radius r is there. So somehow we have to introduce r, that is in radius, into the formula. And we have studied in radius is equal to delta by S, that is area of the triangle upon the semi-perimeter. So somehow we have to introduce the r. And we know semi-perimeter is equal to A plus B plus C upon 2. So in this equation, can we write the right hand side as A plus B plus C upon 2 into 1 by delta? We have written this because we want to convert A plus B plus C upon 2 into the semi-perimeter S. And we know S upon delta is equal to 1 by R. Okay, got it? We have introduced the in radius into the formula. That is the proof of the formula, that is 1 by R is equal to 1 by H1 plus 1 by H2 plus 1 by H3. Here this formula shows the relation between the in radius and the altitude of the triangle. Okay, got it? So these are the formulas that we have covered in this lecture. No need to note down the formula. Just go to the download section and download the formula from the download section. Got it? So that's it for this lecture. Thank you very much for being with Creata classes. Bye for now.